Okay, the topic of today is an overview of Markov modeling or Markov chains. It goes by a lot of different names. And Markov modeling, Markov chains, Markov analysis is actually becoming extremely popular outside our domain. And when I say our domain, I mean process safety and safety instrumented systems, because the mathematics in Markov modeling are the underpinning of all of the artificial intelligence models that you're seeing. So the chat GPTs and the co-pilots of the world, if you look under the hood, they're going to be using the same Markov model math that I'm going to show you to do their calculations, which is massive matrix multiplication and the assumption of stochastic, which is another term I'm going to get into. And it just so happens that when you can do a lot of calculations in parallel with each other, where the results of the calculations don't depend on each other, that's something that a graphics processor can do a lot better than a traditional CPU, which is why if you invested in NVIDIA a few years back, you are really, really, really rich right now. But I digress a little bit. So what I'm going to do is Markov modeling has this mystique, this esoteric mystique to it. Everyone kind of looks at, an advertisement that says, "Oh, we use Markov models," and going, "Oh, that's super impressive. I don't know what that is. It looks real complicated. Must be good." Well, I'm going to try to break that down a little bit and kind of start from the ground up one little bit at a time. And you'll see that it's actually very simple. It's just that when you take a lot of simple things and stack them on top of each other, it can begin to look more complicated than it is. So the subtitle here, demystifying a pretty basic fault propagation modeling tool. And that's the objective. Okay, so why are they Markov models? Because they were invented by Andrei Andreevich Markov, the gentleman to the right there with the kickin' goatee. I gotta say, that's pretty solid. Okay, so Markov modeling is a stochastic process. The model is stochastic. What you're modeling might not be stochastic, which is wherein some of the inaccuracy and some of the over prediction of capabilities comes from. So what does stochastic mean? Stochastic is a word that shows up a lot in academia. It shows up a lot. I'm hearing the word stochastic a lot on the news lately when people want to make themselves seem more intelligent than they actually are. They will use words like empirical and stochastic without actually understanding what they mean. But what does stochastic mean? Stochastic means that the system is very describable or consistent with randomness. Everything about the system is random, and there's a lot of that randomness goes to independence also. So every portion of the model, whether it is the different states or the time sequence of the states, are all completely independent. So what happens in state 1 is completely independent of what happened at state 0. And if you're in a state, movement in and out of that state is completely independent. And what we're going to see is that that's not actually true, especially with the transition from operational state to a failed safe state. When transition to a failed safe state is actually the end of the mission. So more on that coming up after we've gotten into some of the mathematics, but at this point in time, stochastic, random. Everything is random, everything is independent. All the states are all independent of each other. So what we're going to do in a Markov model is we're going to look at probabilities. Now this is the first part that's going to be confusing, because a lot of you have seen Markov models where transitions from one state to another are showing failure rates. They're showing lambdas, or failure rates, for moving into a failed state, and they're showing mu, m, for rates of moving from a failed state back to an operational state. Well, in reality, that's kind of a shortcut that's based on the fact that I'm using a time increment for one state to another, one time period to another, and then using the unreliability equation, or the simplified unreliability equation, that says the probability is lambda times t, and when t is 1, then the probability is just lambda. So we are dealing with probabilities. It's probabilistic. You're basically doing a lot of probability multiplication, is all that's happening in your Markov models. Okay, Markov models are useful. Now, what I'm going to, the big picture message that I'm going to tell you is that Markov modeling has essentially no value in SIS engineering, because we have equations that are going to give you as good or better of an answer than the Markov model. We have analytical solution equations. The value of Markov modeling comes from really complex models, really complex situations where we have a lot of redundancy, a lot of diagnostics, a lot of weird repair schemes that we don't have equations for, and we don't want to take the time to create the equation. So instead of doing a symbolic solution where we create an equation, we're going to basically do a numerical solution, quick and dirty. That's what's happening when you're doing the Markov modeling. Okay, ultimately, simple probability multiplication, and when we get into the number crunching, you're going to see that the use of matrix math is going to allow us to do these calculations very quickly, efficiently, and easily. So a little bit later on, you're going to see me using the mmult function in Excel to run these calculations. Okay, so 101 Markov models. Markov models consist of states, transitions, and probabilities. So a state is a configuration or an instance of the status of the system as a whole. So if you look at a single device, something like a pressure transmitter, a single device, the Markov model will look not too unsimilar to what you see on the screen here. In this case, we have 3 states. So for that transmitter, it could be in the available state, the operational state, the working state. That's going to be state 0. Or it may have failed. And in this case, I'm looking at 2 different failure modes. One is a failed safe, which is going to be state 1, and then failed dangerous, which is state 2. Okay, so we have the different states. Now, this is a very simple model for one component. If you have a multi-component system like a 2 out of 3 vote or a 2 out of 4 vote, you're going to have a lot more states, because you can have a state where the A transmitter is failed safe, you can have a state where the B transmitter is failed safe, and so on. So as you increase the number of components, the complexity of this model is going to expand exponentially, and the difficulty of solving the model also increases exponentially. So first thing you need to think about is, for the system you're trying to model, what are the states that are possible? And that's going to be kind of a function of what failure modes are present. Now, for each state, there are going to be transitions, and the transitions are shown as arcs that will move you from one state to another. So we have an arc here that I'm kind of drawing over with my cursor, that's going to allow you to transition from state 0 to state 1. So that would be a safe failure. So if I'm in the operational state and a safe failure occurs, meaning that the system de-energizes, I'm going to transition from state 0 to state 1. And state 1 is a failed safe state. Now, I can get out of the failed safe state by repairing and going back to the operational state. So I can move in and out of state 1 over the course of a mission, or at least that's the theory. I'll talk a little bit later about why that's not actually true in the stochastic realm of things. So for a failed safe state, you can detect that you've failed safe. You know that you've failed safe. You can repair and return yourself to an operational state. Similarly, you can transition out of a operational state into a failed dangerous state. And in the failed dangerous state, this is what we're going to call an absorbing state. Because in the mission, if you fail dangerously, you can't repair out of it because you don't know that you're in that state. So once you get into state 2, you can't leave state 2. You are stuck there. It's an absorbing state. There are no transitions out. All right, so we have our states, we have our transitions. The next thing we're going to look at is for each one of these transitions, there is a probability per stage, per step, per time increment that we're going to transition from one state to another state. Those are probabilities. They are not failure rates. They are probabilities, and we are going to be doing probability math on them. So whenever you see a Markov model that has a failure rate or a repair rate, you have to understand that that's kind of a shorthand for multiplying a rate times a probability to get an unreliability in a certain time frame. Okay, so we have Markov models, and this kind of, what you're seeing on the screen here can be representative of a 1 out of 1 device that has a safe failure mode and a dangerous failure mode, where you can repair out of the safe failure, but you can't repair out of the dangerous failure mid-mission. All right, now, we are all, or as far as I know, we are all SIS engineers. We are looking at Markov models because we are concerned with safety instrumented systems. But in my explanation of Markov modeling and how it works, I'm not going to talk about safety instrumented systems. I'm going to move us into another realm so that we don't have all of the baggage of our knowledge of safety instrumented systems making things more difficult for us to think about. Instead, I'm going to use Markov models to try to determine where my letter is after I drop it off at the post office. So let's say we live in a world that contains 2 post offices. Post office A is where I live. Post office B is in the location of the addressee. So I'm trying to send someone a letter who lives near post office A. So I am going to take my letter, I'm going to drop it off at post office A, and then I want to know, as a time sequence, at any particular point in time, what is the probability that my letter has arrived at post office B? Okay, so I've got post office A, post office B, and when I start, I'm going to drop off my letter in post office A. Now, in terms of probabilities, I'm going to just use some random rough numbers and say, well, I have a 95% chance that when I drop off my letter at post office A, that same day it will travel and then be located in post office B. 95% of the time, the day I drop the letter off, the next day, 95% of the time, it will be in post office B. But people make mistakes. So there's a chance that, well, maybe once it's in post office B, someone's going to look at it wrong, put it in the wrong pile, and they're going to inadvertently send it back to office A. And I'm going to put a 2% probability on that. So the first thing we're going to do is we're going to draw our Markov models. So state 1, so there are two states. Either the letter is in post office A or the letter is in post office B. It's going to be in one of those two states. And in the very beginning, if I'm only looking at post office A, what is the possibility or probability of transition? So transitions is something I'm going to talk about more because that's an integral part of solving the Markov models. So at time 0, when I drop the letter in post office A, there's a 100% chance that it is in office A, and there's a 0% chance that it's in office B. So a little bit later on, I'm going to talk about something called a state matrix, but for right now, I know that at time 0, my state matrix is 1.0, 0.0. Which means there's a 100% chance that it is in post office A and a 0% chance that it's in post office B. The next thing that I looked at again are the transitions. So I know that if I'm in post office A, there's a 95% chance that I'm going to transition to post office B. But the unspoken part of that statement is that if there's a 95% chance it transitions to post office B, then there's the complement, 1 minus 95%, or 5% of the time, it's going to stay in post office A. So the transitions, when you look at any particular state, and let's call post office A a state, all of the probabilities of transitions need to add up to 1. So what we're going to see is that the probability of staying in a state is 1 minus all of the probabilities of transitioning out of the state. More on that when we start talking about a specific instrument. Okay, so that's what you're looking at in at day 0. So at day 2, at day 1, because day 0 is when I drop it off. Day 1, which is the next day, there is going to be a 95% chance that it's going to be in post office B, and there's going to be a 5% chance that it's still sitting in office A. And the way we're going to draw that using our Markov model terminology is that the state vector at time 1 is going to be 0.05. Let's try that again. 0.05, 0.95. So 5% chance that it's in post office A, 95% chance that it's in post office B. Let's continue. Now at day 2, I said that there is a chance, and again, I'll write this up here. So the state vector at day 1 is 5% A, 95% B. But I can still transition. Post office B is not an absorbing state because someone can accidentally send the letter back to post office A because they put it in the wrong pile, they misread it, whatever reason, there's a 2% chance that it's going back to post office A. So if there's
we got a couple questions out there.
Sure. All right, go ahead and give them to me.
The first one is, does this assume that only one transition is allowed in one day, meaning that it is not possible that the letter move from A to B and back to A in one day?
That is absolutely correct and absolutely true. That's an artifact of how Markov modeling works. And that's one of those things where it may not be true in reality, but that is absolutely the assumption. Only one transition is going to occur in the day. Okay, so kind of going back to that some of the probabilities have to go to unity. If there's a 2% chance that it goes back to post office A, then there's a 98% chance that it's going to stay in office B. So what we need to do is, in order to get the state vector at time 2, you need to do probability multiplication. So in order to determine the probability that I am still in the A, and I kind of, I need to get my probability math correct here. But so the probability of being in state B, still in the post office on day 2, is 0.95 times 0.8 plus 0.05 times 0.95, which is going to give me a probability of 0.9785. So now, how did that work? So if I look at the probability of being in post office A, so it started out at the beginning of day 1 as 0.5, and then there's also a 0.2 chance that it, or a 0.2 chance that it's going to get sent back to post office A. All right, so this is kind of the details of how it works. Now, and I'm going to show you the mathematics a little bit more 2 slides from now in terms of how it's actually solved, because you're not going to do strings of hundreds of probability multiplications, and I'll show you what you're actually going to do. But now, in the world, there are more than 2 post offices. So what if instead of just post office A, I have a B, I have a C, and I have a D? You can see with all those crazy arrows for transitions that you see on the screen that the math and the logic is going to get really complicated, because you need to think about every post office and every possibility of correctly or inadvertently sending a letter to a different post office. So as the number of post offices increases, the calculations are going to increase exponentially. The math gets crazy. Okay, so let's make the math a little bit easier, because ultimately when you solve these things, you're going to use matrix math calculations to do the solutions. So we're going to start out with 2 things. There's going to be a state vector that I've already introduced, and then there is going to be a transition matrix. So for a state vector, and at time 0, I already mentioned that the state vector is 1, 0, meaning there's a 100% chance that the letter is in post office A. There's a 0% chance that the letter is in post office B. At time 1 day after I drop the letter in the post office, the state vector changes to 0.05, 0.95, because there's a 5% chance that the letter is in office A, and then a 95% chance that the letter is in office B. And these numbers are going to continue to change with every time increment, every status change. I'm showing Markov models here, and the way we think about Markov models when we're doing SIS engineering is in terms of time increments. But when you're using a Markov model for artificial intelligence, it's not time increments. It's other status changes that you're running the calculations for. So state vector is for each system increment, whether it's a time increment or something else. So if you're doing this by the hour, for instance, which is what we're going to end up doing for our SIS engineering calculations, you're going to need to do this. Let's say you want to know your system over the course of 1 year. So in order to know the performance of your system over the course of 1 year, you're going to need to look at 8,760 different states in order to come up with the final number that you're concerned with. So those are state vectors. The next thing that we're going to do is we're going to put together a transition matrix. So a transition matrix is going to include all of the states as rows and all of the states as columns, and then put in the probability for each time step that you transition from one state to another state. So if I am in post office A, the probability that I stay in post office A is 5%. If I'm in post office A, the probability that I move to post office B is 95%. And if you add the numbers together, you're going to get to 1.0. Okay? It's similarly to B. If you're in B, the probability you transition to A is 2%. If you're in B, the probability you stay in B is 0.98%. So that's how you develop your transition matrix. So state vectors, probability of being in any particular state. Transition matrix is all of the combinations of moving from one state to another or staying in the state that you're in. So number crunching wise, how do we calculate the probability of one state or the next state, given that you know the probability of the current state and the transition matrix? Well, it's a simple multiplication. So if I want to know the state matrix for time increment 1, I plus 1, I need to know the state vector for time increment 0, and I multiply that by the transition matrix. So it's a simple matrix multiplication. And in the modern world, we don't need to worry about how you actually do the matrix multiplication by hand because we have Excel. So in Microsoft Excel, the formula name is mmult. So mmult is the formula, S is your state matrix, T is your transition matrix. So when I shoved our post office problem into Excel, I gave it a state vector here, I gave it a transition matrix here, and then when I did the formulas, I simply did the calculation of state matrix 0 or state vector 0 against the transition matrix to get this number, which is exactly the same as we got when we did things by hand. Day 2, you're going to start with the state vector for time stamp 1, multiply by the same transition matrix, and lo and behold, we're getting the same numbers as when we did the math by hand. And we were able to do the math by hand because we only had 2 states. So if you then plot versus time, so this is kind of I honestly, I screwed up when I was doing the doing my graph here, but the shape is kind of what I wanted to show you, where you're basically getting an asymptotic approach to 0.98 as time increases. As a matter of fact, we kind of get stuck right here at day 4 with a 97.9 probability at any particular day after day 4 that my letter is in post office B. Okay, so that's kind of the big picture overview of how you build a Markov model and how you solve a Markov model using something, an example that takes you out of the realm of SIS engineering and lets you kind of just focus on the mathematics of what's happening. Okay, now let's go and do this for SIS engineering. So the first step in developing your Markov model is going to be to know what the states are. And how do you know the states? The states are, there's always going to be an operational state where no failures are present. And then the balance of the states are going to be failure modes. Now, if you've taken the EC50 class, if you've read the 61511 standard or any book about SIS engineering, you have had it beaten into your head that there is failed safe and there is failed dangerous. Well, failed safe and failed dangerous are actually more akin to effects than failure modes. And they allow you to actually collect a bunch of failure modes together that will put the system in a certain state. So if you think about failed state, that's going to be we're de-energized or our contacts are open. Now, there may be a lot of different physical things that can happen to cause you to go into the de-energized state where your contacts are open. So maybe you disconnected your power. Maybe your solenoid coil has gotten a lot of short circuits and it's not creating enough magnetism to close the circuit anymore, and then the contacts go open. What I'm going to talk about a little bit later in terms of the value of Markov modeling is that sometimes you don't want to lump all of your safes and all of your dangerouses together, and you want to look at them a little bit more granularly. But for right now, let's just kind of focus on there's a safe state and a dangerous state. And that dangerous
there's another
state,
question out there
sure,
before you get
go
too
ahead.
much further. On the previous slide, in the graph on the matrix mass slide, the PA and PB curves would be inverses of each other?
They would look inverted. So yeah, the PA is going to be kind of look more like this, and the sum will always go to 100%. Because you have to be in one state or the other. That is correct. Okay, so back to building the Markov model. So define what your states are: operational, failed safe, failed dangerous. Now, what you're looking at here is this is for a simple 1 out of 1 system. As you add more components, you're going to get much more complex real fast. Because then you need to say, okay, state 0 is when, like in a 1 out of 2 vote, state 0 is when both of my devices are operational. State 1 could be the A devices failed dangerous. State B could be device 1 and 2, or A and B are both failed dangerous. So the number of states is going to grow exponentially as the number of components grows. All right, but kind of nailing it down for our 1 out of 1 system here, we have operational, we have failed safe, we have failed dangerous. The next thing we need to do is we need to define the transitions. So if I'm in one state, and I need to think about this for all of the states together. So you start at state 0 and say, is it possible for me to go from the operational state to the failed safe state? If the answer is yes, then you draw your transition arc. If I'm in state 0, if I'm operational, is it possible to go to state 2 or the dangerous state? Yes, that is possible. So, come on. So I'm going to draw that transition. And then you repeat this process for every state. So if I'm in state 1, is it possible for me to go to state 0? Yes, I could do that by repairing. Is it possible for me to go from state 1 to state 2? Well, most Markov models that are used in industry will tell you, no, this is not possible. We don't need to model this. You can't go from a failed safe state to a failed dangerous state. But in reality, is that actually true? I am aware of several instances where the action of trying to repair a failed safe component resulted in that component being failed dangerous because there were human errors in the repair process. So that's kind of questionable whether there isn't a transition from state 1 to state 2. But since we're looking at random hardware failures and we want to make our life easier, we're going to assume no, we can't get from state 1 to state 2. Now, from state 2, can you go to state 0? Well, mid-mission, and I'm going to talk about mission on the next slide in a little bit more detail. Mid-mission, no, you cannot go from state 2 to state 0 because you don't know that you're in state 2. You can't repair out of a dangerous undetected failure because you don't know that that failure is present. So you will stay in state 2. It is an absorbing state. Now, can you go from state 2 to state 1? So failed dangerous to failed safe? Well, most SIS engineers will model it such that you can't. But in reality, yeah, you probably can. So if you look at a electromechanical relay, if the contacts weld, that's a dangerous failure. So you go from state 0 to state 2. But if then the wire disconnects, the wire that applies power to that solenoid valve, if that wire disconnects, you've just gone from state 2 to state 1. So this is a transition that is not modeled in anyone's Markov models when they do Markov modeling. But in reality, there's actually a probability that you can go from dangerous undetected to safe failure. So lots of crazy things to think about, but what we're looking at on the screen here is going to be your typical 1 out of 1, no diagnostics type of situation. All right, so now that I've built my transitions, I can quantify my transitions. So I know what my states are, I know what my transitions are. I now need to put probabilities. So when you look at the screen, you see what is typically shown in a Markov models, which are going to be lambdas, which represent failure rates, and mu's, which represent repair rates. So I kind of started off by telling you this is not true. It is not a rate. It is a probability per increment. Now, the reason that the shorthand is to show failure rates is that the rates are going to be in units of per hour, and my time step is an hour. And when I calculate out my probability of transition, so my probability of transition is going to be my failure rate times delta t. If delta t equals 1, then my probability is going to equal the rate. So don't think it's the rate, it's a probability. It's just that there's kind of some simplifying assumptions for people, for the brotherhood that does this kind of stuff, that we're going to use 1 hour and my failure rates are in per hour. So I can ignore that delta t when I do my probability calculation. And it is going to be a traditional unreliability calculation. Okay, so yeah, that's why you show that. So we've got lambdas for transitions from operational to failed. We have mu's for transitions from failed back to operational. So now we go and we do our numbers. So to start off the process, before we do any matrix multiplications, we need to define our state vector at time 0, and we need to define our transition matrix. First, let's do it symbolically before we put numbers in. So the state vector needs to be at time 0, the probability of being in state 0, the probability of being in state 1, and the probability of being in state 2. In our SIS engineering, we assume at time 0 the device is actually working. Is that always true? Well, not necessarily, but universally we assume that, well, we just tested it, we know it's working, so we're going to put a 1 probability on being in state 0 and a 0 probability in being in states 1 or state 2. Then we build up our transition matrix. So our Markov model is over here again, and we're going to start by putting down the numbers for state 0. We're not going to start with the transition from state 0 to state 0 because that's going to be an artifact of our calculation. So to get from state 0 to state 1 is lambda s. To get from state 0 to state 2 is lambda d. So what then is the probability of staying in state 0? For each row of the matrix, it needs to sum to 1. So if I've got lambda s and I've got lambda d, then the probability of staying in state 0 has to be 1 minus the sum of everything else, or lambda s plus lambda d. Need to fix this slide, sorry about that. Okay, we do the same thing for the other states. So when I go to state 1, now I'm in state 1, I can get to state 0 by a probability of mu. The probability that I could get from state 1 to state 2 doesn't exist, so that's going to be a 0. And the probability then that I stay in state 1 is 1 minus the sum of all the other transitions, so now I'm back to 1 minus mu. For state 2, the probability of transitioning from state 2 to state 0 is 0. Can't do it. The probability of transitioning from state 2 to state 1 is 0. Can't do it. So that means the probability that once I'm in state 2 that I stay in state 2 is 1.0. So there's my transition matrix. Now, if I were a sane and if this system was going to be present, or I'm going to use this system a lot, instead of numerically solving my Markov model, I could just solve my Markov model with these symbols and come up with an equation. And guess what? When you use the analytical solution equations that are present in the ISA technical report on SIL verification calculations, that's what you got. You've got an analytical solution. But when you use a Markov model, you're actually doing a numeric approximation of what the analytical solution equations will give you. Okay, so now if I put some numbers in instead of solving it analytically, you'll see this is my lambda. My lambda d is 2 minus 6. I'm sorry. More corrections to make. So my lambda s is 2e minus 6. So this is lambda s, this is lambda d. This is going to be mu, or I'm just assuming a mean repair time of 50 hours to give me nice round numbers. And that's how you fill out your transition matrix. So then what I want to do is I want to use this Markov model to calculate the probability that I am in the failed state. So what is the probability that I am in state 2, which is my dangerous undetected? That's what my SIL verification calculations are based on. State 2, bad. So what is the probability that I am in state 2 at the end of 1 quarter, at the end of 3 months, which is 2190 hours? And I did this for 2190 hours because when you see the spreadsheet, I mean, I need a row for every hour, and I didn't want to do that much clicking. So I limited it to 1/4 or 3 months. So what the spreadsheet is doing is you're taking your state vector, you're multiplying it by your transition matrix, and you're doing that once for each hour. So after the first hour, this is the probability I'm in state 2. After the second hour, this is the probability that I'm in state 2. And you do this matrix multiplication 2,190 times to know where you're at the end of 3 months. And the answer is the probability that you're in state 2 is 2.18739 E minus 3. But when we're doing SIL verification calculations, we don't use the instantaneous probability of failure on demand. We use the average probability of failure on demand. So basically, we're going to add all 2,190 of those numbers together and then divide by 2190. Its arithmetic mean is going to be 1.0946 E minus 3. So roughly 2,000 matrix calculations later, we have 1.095 E minus 3. Well, if all we would have done is used that simple average unreliability calculation, lambda t over 2, guess what? One multiplication got us to effectively the same number. In both cases. So if I just multiply lambda t, I would have got to 2190. That's the max. Lambda t over 2 gets me here. So why the heck am I going, and this is for 1/4. If you want to do this for 1 year, I'm doing 8,760 matrix multiplications to get to a number that I could get to just as accurately by multiplying 2 numbers together. So as you see, this is very time consuming and it's very computationally intensive. Oh my goodness, think of the carbon footprint of what we just did. All those multiplications, all that CPU time, for what? Okay, so basically what I'm trying to impress upon you here is that if you have the equation, and you can get the equation by doing an analytical solution of this Markov model instead of what you see here, which is a numerical approximation. And so basically it's an approximation, but as the time increment approaches 0, the numerical solution is going to approach the analytical solution. So just, something to think about from a calculation perspective, kind of the definition of an integral, if you will. As that delta t goes to 0, you're going to approach the integral. All right. So, wow, it seems like much ado about nothing. Well, let me make things a little bit more complex for you and tell you about some of the assumptions that you're making that aren't actually true. The first one of these is going to be the assumption related to the failure rate. So we all know that we're going to assume that the failure rate is constant. And basically we feel comfortable about that because we know that the reality is the bathtub curve. And we say, well, if we throw away infant mortality, if we throw away the wear-out failure regime, we're going to be pretty close to a constant failure rate. Okay, that's reasonable. But in a Markov model, well, pretty much any of the reliability models that we're using, the idea that the repair rate is constant is fanciful ridiculous. Okay, so what the Markov model is telling you is that it is just as likely that I will repair my device at hour equal number 1 as I will at hour number 100. That is ridiculous. That does not match reality in any way, shape, or form. The reality is that your probability of repair is going to work on this sort of log normal. So there's a certain amount of time where it is physically impossible to make the repair faster than a certain time period. So if you need to replace a valve, if you've failed a valve, my goodness, you're going to need to get work orders, you're going to need to get spare parts, you're going to need to remove the current valve from service after you've bypassed it, you're going to put the new valve into service, replace all the top gear and test it. I'm sorry, but that cannot happen in 1 hour. It's physically impossible. But once you get past that threshold of physical impossibility, it's going to shoot up real fast to get to this number for mean repair time. And then once you do that, now we're going to have more of the Gaussian decay, where as time increases, the probability decreases because you probably repaired it earlier, and it gets closer and closer to 0 as time approaches infinity, because, well, the probability of something just not getting repaired when you know that it's failed becomes kind of obscene as time increases. Now, in a Markov model, the lambdas are really small, but the mu's are really big. And that could give us, I'm not going to say that it kind of throws Markov models off the table in terms of realism, but it's something that you really need to think about as you're developing these models, because that repair rate, not only is it not constant, there's no argument to justify that it can be constant. It's one of those things where the reliability engineers really just kind of have to look the other way when they're running their calculations. Okay, so
another question, Ed.
Sure, absolutely.
How is the PFH calculated instead?
Okay, how is probability of failure per hour calculated? So probability of failure per hour for a component is going to be basically your failure rate times delta t, which is going to be 1 hour. So this is a standard unreliability equation. And in terms of unreliability, I'm not prepared to discuss the definition of unreliability. This lambda t is already a simplification in and of itself, because you're actually looking at 1 minus e to the minus lambda t, and the definition of e is all related to integrating into a time interval equals 0. You're basically integrating a probability density function, is how you do it. So when you're calculating PFH, you're integrating your probability density function for 1 hour. And again, you have to assume that your failure rate is constant over that hour. Otherwise, you're going to run into those same error issues. Now, instead of having lambda be a constant, it's possible using things like the Weibull distribution to make your lambda time variant when you're running these calculations. But that level of complexity, that level of detail, is something that I have never seen applied to the domain of SIS engineering. Okay, so I've talked a lot about how to build Markov models, and I basically said, if you have an equation, all you're doing is tens of thousands of calculations instead of one to effectively get to the same point. And I kind of also, and I need to kind of brush up on this point a little bit. Um, I kind of have to question the validity of the stochastic nature of what you're doing, specifically right here. So when you think about a mission, the term mission in reliability engineering really came from the military. So a mission would be something like, I'm going to send a plane out to drop bombs on a target, and then the plane's going to come back. So the plane leaving, flying to its destination, and coming back is the mission. And over the course of that mission, what are the reliability engineering constraints? And for that mission, the system state is constant, so the plane is flying. If I have a spurious trip, I'm going to argue to you that things are not stochastic anymore. Our system state has changed. The plant has shut down. You can't say that nothing has changed. Keep running your calculations. That would be like the plane falling out of the sky and you still running calculations on it. Okay? It's not stochastic anymore after that spurious failure has occurred. After the failure has occurred, time increment +1 after that failure is going to be wildly different and wildly dependent on what just happened in the previous state. So that's another kind of consideration when you're thinking about and looking at these Markov models. So
there's another question in the chat there, Ed.
Sure. N approximately if dt equals 0 or dt equals infinity. No, the time increase. So if you think about the definition of an integral, it started out as Riemann sums. So we're going to take a function and we're going to analyze the function piecewise, and we're going to pick one value of the function and add up the sum as we do the stepwise function. Now, as the size of that increment approaches 0, the number is going to reach its most accurate state. So we want the time as the time increment, the delta t approaches 0, you're going to achieve the highest level of accuracy. So if you want to go ahead and look at the definition of an integral, that's where this thought process comes from. Okay, so kind of going back to the advantages. Now, I don't want to say that Markov modeling is useless. It definitely is not. There are a lot of people who are using it for a lot of very important purposes. My goodness, artificial intelligence as we know it today would not exist without Markov models. So but then I also said it's pretty damn computationally intensive, and if you can do an analytical solution to get an equation, that is the most accurate and the most cost-efficient way in terms of computational intensity to come up with your answer. So now, what are some reasons that you would use a Markov model? Well, making the discussion very succinct, you may want to use a Markov model if you have a complex situation that you don't have an equation for. So what are some situations where a Markov model is very effective? So what a Markov model can do very efficiently that other tools and equations can't is model failures being present at time 0. So going back to our analysis, if I have a state vector, I can put in that, well, there's a 95% chance that I'm operational, but there's a 5% chance I'm in the dangerous undetected failure state at time 0. So that's something that you can't really put into your standard set of equations. The other thing that makes Markov modeling very valuable especially in the modeling of SIS logic solvers, is that you're going to be allowed to handle different failure modes in different ways. So if I have a logic solver, there may be different failure modes. And now I'm not talking about just safe or dangerous. I'm talking about the specific mechanical failure that caused you to get into the failed state. So for instance, there may be a failure mode where a cosmic ray from outer space flipped a bit in memory. That could be a dangerous undetected failure mode. Well, that failure can be essentially 100% detected by inverting the memory map and comparing the memory map and the inverted memory map and seeing whether or not they're mirror images of each other. And then the repair of that failure could happen in one scan. You simply wipe the memory and start over again. You basically wipe the image. So that memory bit flipped can be repaired in 100 milliseconds. Whereas another failure mode, so let's say that a capacitor on the board burned out and gave you an open circuit. That could be a dangerous failure, but that failure might require you to replace the card in the logic solver, and that failure mode might take 48 hours to repair. So these different failure modes have different detectability. Maybe it's 100% detectable, maybe it's only a 50-50 shot that my diagnostic will be able to detect that that failure mode is present. And for that particular failure mode, maybe I can repair it in 100 milliseconds, maybe I can repair it in 48 hours. So it's this kind of complexity that your equipment vendors are looking at when they're doing the probability of failure on demand calculations for their logic solver systems. So they are going to create extremely complex Markov models to perform these calculations that have lots of redundancy, lots of different failure modes, lots of different detectabilities, and lots of different repair rates depending on what the failure mode is. So that's why you go to a logic solver, and if they have a certified device, you ask them how they calculated the probability of failure on demand. The answer is probably going to be a Markov model, but that's because their logic solver is very unique and very custom, and it doesn't really make any sense to try to develop an equation for that complex system that they have. But if you've got a standard 2 out of 3 vote of a pressure transmitter, there is an equation for that, and you don't need to develop a Markov model. All right, so one last note on Markov modeling. So as I mentioned, a lot of the equipment vendors have Markov models for developing their logic solvers. Now, as you know, if you run Markov models, the probability that the SIL3 certified logic solver is the weak link in your calculation is effectively 0. Most of the time, the PFD of the logic solver is much smaller than the significant digits of the calculation as a whole and disappears from the PFD of your safety instrumented function. But if you do want to run models of your safety instrumented system logic solver, you're probably best off not modeling it yourself, and you're probably best off not modeling it in a packaged software application, no matter how much the equipment vendor or the software vendor tells you how accurate that their models are. And the reason for that is that these Markov models that are developed by the equipment vendors are super highly proprietary trade secrets. And they are not going to give these Markov models to the vendors of SIS software so that you can run the calculations yourself. Okay, so we at Kenexis, we have our Vertigo software, which is absolutely best in class for SIS design basis development. And we have had conversations with all of the major equipment vendors on how to model their application. And if you go to a, like an Emerson has given us equations. They said, use these equations in your software for modeling our system, and we respect that, and we run those equations that are based off of their Markov models. But companies like Schneider with Triconics and Siemens tell us, we don't want you modeling our logic solver in your software. We don't want our end users modeling our SIS logic solvers. Instead, we want our customers to come to us, and we will tell them, we will run the calculations, we will give you a PFD, we will give you a spurious trip rate to use in your calculations. And if you're using Kenexis's Vertigo tool, you'll take that PFD, you'll take that spurious trip rate, and you'll enter it in as what we call a black box model, where regardless of the actual underpinning of the system, test intervals, and all that other fancy stuff, you're just going to enter in the PFD and the spurious trip rate as a system as a whole. And most of the equipment vendors out there for their SIS logic solvers, that is exactly what they want. They don't want you diddling around and trying to put failure rates into a 2 out of 3 equation and hoping for the best. Because as we have just shown here, they have developed Markov models because their systems are so complex, and they keep those Markov models close to the vest, and they don't share them with people like, well, sometimes they share them with us, but for the most part, they don't share them with the software vendors of SIS SIL verification software. All right. So
another question, Ed.
Yes.
Another question.
Yes.
The existing formulas for M out of N architectures you are referring to are the ones derived from FTA or RBD?
They can be derived. You can derive them from a symbolic solution of fault trees. You can derive them. I mean, anything that you can solve from fault tree analysis, you can also solve as an unreliability model or unreliability block diagram. They're just different ways of visually showing you probability math. At the end of the day, there is an equation that's going to be based on the logic and integration of that logic over a time series to come up with probability of failure on demand, average probability of failure on demand. So it really doesn't matter what graphical tool you use to demonstrate what your logic is. They should both give you the same logic, or they should all give you the same logic. And then it's just a matter of solving that logic or simplifying that logic into an equation.
Okay, another question in the chat. One common advantage commonly given for Markov models is the fact that more external factors can be considered while modeling. How so? Factors like beta factor or site safety index or mission time. Are they more states in the model?
Not really. So the Markov modeling, a lot of what was just brought up there actually isn't in the Markov models themselves. So the things like the site index is a factor that is intended, using some qualitative hocus pocus, to try to modify your failure rates as a function of how you treat your devices at your site. So a site that has really good maintenance practices is going to have lower failure rates than a site that doesn't have really good maintenance practices. And in reality, if you wanted to model that, then you should be using your site's failure rate data instead of trying to use some sort of hocus pocus to model a predictive FMEA and map that to how that FMEA number would change based on the quality of the maintenance that's occurring at the plant. So that kind of site index is actually modifying failure rates. It's not adding or changing states in the Markov model. Beta factor is I didn't show a Markov model that had a common cause failure state, but you can model a common cause failure state in any fault propagation model. Fault trees, reliability block diagrams. There's nothing unique about how a Markov model handles beta factors that can't be handled in any other model. So I think a lot of what was stated in that question is one particular software vendor's attempt to make their software seem better than everyone else's, and it's not really an inherent attribute of Markov models themselves.
Okay, thank you.
Okay. All right, so wrapping up a little bit in terms of conclusion. So Markov models are valuable. They are going to allow you the assessment of complex repair, complex redundancy schemes, different handling of multiple different failure modes that aren't available in the standard equations. Now, you can always develop equations by simply doing a symbolic solution of a Markov model, which describes the logic from getting from one state to another. And that symbolic solution is not going to be significantly different from any other fault propagation model. Solution of Markov models numerically, which is everyone who uses Markov models is going to solve them numerically, is very time intensive, very computationally intensive, several orders of magnitude more computations than just using an analytical solution equation. Markov models are unnecessary where analytical solution equations are available, and this is virtually the case with all end user applications. So as an end user, what you're modeling, there is generally going to be an analytical solution equation available for your use that's going to give you the same answer with tens of thousands of less calculations required to get to that state. So with that, I know I've been answering questions as we've gone through the presentation, which is what I like to do. I like to make things a little bit more conversational. But at this point in time, I have kind of reached the end of my canned presentation, and I'll open up the floor to any other questions that might have come up. You can shout them out, or you can type them in the chat, whatever you want.
Okay, there's one in the chat. Does Markov modeling take into account systematic failure rate as well?
You can. Any fault propagation model has the ability to model systematic failures, systematic human failures. Now, this is, I don't want to go completely off topic, and I think either we've had a webinar on this, or I've got up on our board that we need to do another webinar on this. I am going to highly discourage you from modeling systematic human failures when you're calculating probability of failure on demand. So if I could, I'm going to open up my copy, which is the current copy of IEC 61511, which sits always on the top drawer of my desk. And I'm going to go into clause 11.9. And 11.9 is all of the information about performing SIL verification calculations. The section is called quantification of random failure. Whoa, right in the title. Right in the title, when it's talking about PFD, the title says quantification of random failure. So right out of the gate, you should be asking yourself whether or not I should be modeling systematic failures. And the standard is pretty damn clear that the answer is no. And it will actually lead you to the wrong answer, and I'll get into that in just a second. But it says, 1191, the calculated failure measure of each SIF shall be equal to or better than the target failure measure, okay? And then it says the calculated failure measure shall consider, and it says estimated failure rate of dangerous detected. So 11.9.2b is you need to consider DD failures due to random hardware failures. Clause C says that you need to consider DU failures, which are due to random hardware failure, and then DN failures, which are due to random hardware failure. Everywhere there, when it talked about failure rate, it said random hardware failure. It did not say anything about systematic failures or systematic human failures. Why is that the case? Why are we performing SIL verification calculations? We're performing SIL verification calculations to determine whether the architecture and test interval of the equipment that we selected is appropriate. Well, if you don't achieve your SIL target, so let's say I took the systematic failure rate of my technician miscalibrating a transmitter, lambda miscalibration, and I'm going to put that into my SIL verification calculation. So I've got lambda DU plus lambda miscalibration. I'm going to plug that into my SIL verification calculation, and all of a sudden my 1 out of 1 voting arrangement for my transmitter doesn't allow me to achieve SIL 1 so let's say I'm shooting for SIL 2. I'm not able to achieve SIL 2 anymore with my 1 out of 1 voting arrangement. What am I going to do? I'm either going to add redundancy, make it 1 out of 2, or I'm going to increase my test interval to bump that PFD up. Did that fix the problem? No, it didn't fix the problem at all. So increasing the test interval just gave my technician more opportunities to make that mistake. And did my redundancy help me? No. If the technician miscalibrated the first device, they're going to miscalibrate the second device too. So adding in systematic human failures into your SIL verification calculations not only does not fix the problem, it actually makes things worse. It leads you to improper solutions. So I kind of got off on a little bit of a tangent there, but no. While any fault propagation modeling tool will allow you to model systematic human failures, I strongly encourage you, in full conformance with the IEC 61511 standard, not to model systematic human failures when you're doing your SIL verification calculations. I love it when I get a question that allows me to go completely off topic. Anything else, Chris?
Well, there's one out there that says maybe off topic. I think the M out of N architecture formulas of 61508 are derived from an RBD or something similar. So it is correct to say that in industrial applications, if we can reconduct the system to an M out of N architecture of the 61508, the Markov modeling is always unnecessary.
Yeah, exactly. That's kind of the big point, is that For a standard M out of N configuration, we have equations. So there's no reason to do this really complex numerical approximation when we have an analytical solution equation. The only time that it makes sense to do this complex numerical solution is if we don't have an equation. And what are the situations where we're not going to have equations? Well, when we start in a failed state, well, I don't have an equation for that. When I've got 10 failure modes, each of which have different degrees of detectability and different repair rates, I don't have an equation for that. So in that case, yes, go build a Markov model and solve it numerically. That makes sense because you have a very unique situation. But if that's not the case, it's infinitely more efficient. That is the word for today that describes all of Kenexis' software, the Kenexis Integrated Safety Suite. The most efficient way to get your technical safety tasks done. It's definitely going to be more efficient to use analytical solutions equations if they're available. If they're not available, then you need to dig into the toolbox and use something a little bit more sophisticated.
I think we have one more out there.
Okay.
For reference, do you have a slide showing the state transition map and state vector versus transition matrix for a 1 out of 2 system?
Not at my fingertips. What I would recommend, if you really want to see all the Markov models, the ISA EC54 course has a book associated with it that was written by Bill Goebel and Iwan van Beurden, and it goes into all of the detail on the Markov models for all the standard configurations. So I would point you to that book, and if you took EC54, you already have the book to go into that level of detail. I don't have those at my fingertips because, again, this is not something I feel the need to teach to most people, because I think what I've recognized is that the only time that I use Markov models is when I need to do a technical acumen flex at a conference or something to say, yeah, I know how to solve these things too. But because nobody uses them day to day in practice, I never need to teach them.
It is safety instrumented system design, techniques and design verification by Iwan van Beurden and William M. Goebel, CFSC. It's an ISA publication.
That's the one. It is an ISA publication, absolutely.
I had one more question, Ed, is if we were to model shared systems to check out the common cause failure, let's say we have a BPCS sharing components with SIS, what is the best modeling method for those kind of applications?
Okay, so if you're sharing components between the basic process control system and the SIS, your problem is dramatically more complex, because now the probability of failure of your safety instrumented system is just one piece of the overall risk puzzle. So if you're sharing components between SIS and BPCS, the PFD of the SIS instrumentation is commingled with the initiating event of the hazard under control and the probability of failure of the other independent protection layers other than the safety instrumented system. So that sharing is not just SIL verification. That sharing goes into the hazard and risk assessment, the layer of protection analysis, the overall analysis of risk of the plant. Now, I have never seen anyone, and don't expect to ever see anyone, try to do a hazard and risk assessment of a chemical process using a Markov model. How you would model that kind of sharing is using fault tree analysis, where you can take the shared components and separate them out from the rest of the components of the SIS, and the fault tree will elegantly handle the fact that this shared component shows up in the initiating event, shows up in the SIS, shows up in other non-SIS protection layers. So that topic is the topic of an entirely separate webinar that we did probably 4 months ago. So I would encourage you to look at the Kenexis website, look at our recorded webinars page, and find the recorded webinar that talks about using fault tree analysis to supplement layer of protection analysis. And that there's another 2 hour webinar for you. Thank you everyone for your attendance.